Still, we know nothing about the underlying CFT. We're just going to build it for all of them. At least on 2D, we're able to do that. But let's recap. There are things we have learned that's important still today. For example, our favorite cylinder to plane map. So remember, the important thing is this is the time direction, a Euclidean time direction. And there is an equal time surface, gets mapped to some equal radius circle. And we keep emphasizing this place where time goes to infinite past, gets to map to the origin. And today, this transformation you have seen in the tutorial is actually important. So let me write it. So they propose, if you do this, take a cylinder, it will be mapped onto a complex plane. Hey, we have seen this before. We also seen this a lot of times already. It says that if I have two primary fields, then I can very happily write down the two-point correlation with some normalization constant. I don't care. So I guess in this case, I'll just take it to be two of the same kind of primary operator. Okay? And then what we further learned yesterday is that it seems a good idea to expand the energy momentum tensor in terms of its Laurent modes, because these are our generators, which we spent a whole class to figure out the quantum version of the conformal algebra has some extra term. So, well, the Cauchy formula is still there, and we'll do some contour integral as needed. So that's where we are at. We find an algebra. And as I keep emphasizing, that's what we always do. After we find the algebra, we want to find the representation of it. Okay, so since we're going to build a Hilbert space, it's intuitive that our first step to define what is our in state, or you might heard about it as the asymptotic past state. So your initial state from QFT, something you prepare some state and ready to do some scattering. And sometimes it's called the in state or initial state. And you want to build the out state. So in the infinite future, what happens? Some good things to define. And after that, we're going to study our vacuum. When there is vacuum, and we just want to know, in general, for all the 2D CFT, what would be the property of the vacuum. And the next step, we're going to build a highest weight state. I hope you are still familiar with what's highest weight. And it's labeled by the conformal weight. Highest weight. Weight means eigenvalue. Highest weight. Okay. In this particular case, it's slightly misnomer. But it's some state. It's like in the spin 1 representation, the spin 1 state. Then you can build on top of it and get all the rest of the states. Okay. After we find our highest weight state, we can find all the descendant that you probably already heard. State. space. And after we do that, well, that's the Hilbert space. You'll find the entire representation. What else you ask? So after that, we begin to talk about a miracle. This miracle is a claim. The claim is only correlation functions of primary operators matter. Okay. That's good. That's why they are called the primary operators. And with a few more miracles, we'll be able to find out why the 2D CFT, at least trying to find the minimal ones, the easy ones. It's easier to find the solvable ones compared to in other dimensions. Okay, so first thing, before we define the state, well, what am I supposed to do? The only thing so far I learned up to today is a bunch of primary operators. Okay, on top of that, there is the energy momentum operator. How am I supposed to get a state of it? Well, you might have heard of this. In CFT, there is something very special called the state operator correspondence. To be technically correct, it should be local operator. Okay, so this is something bizarre in QFT. Think about it. So in QFT, what we learned is there is something called one particle state, and it's something like a creation operator acting on a vector. And this is called a one particle state with a certain momentum k. And if you write down what's the momentum operator, it's something entirely non-local. It's highly non-local. It actually depends on everywhere. And now you're telling me that the state and the local operator can have a correspondence. This is insane. And if you think about the QFT in the other direction, it's still insane. So this is what we call a local operator in QFT. It's basically a field. Says, hey, look, I depend on the location. Hence, I'm a local operator. And now if you want to ask, what's a state in QFT? It's a wave function. And this wave function is a functional depend on the entire spatial slice of whatever space we care. So it's something like this. So this is really the entire space. So you're saying something dependent on one point is corresponding to something depends on the entire space. You're like, you're crazy. Well, yes, in QFT, such correspondence doesn't exist. But in CFT, one thing makes it possible. Because we have conformal symmetry, which means, and once upon a time, the spatial slice is mapped to a single point. Which come back to our cylinder, when we go to the infinite past, on the cylinder we still have a space that is extended. But on the complex plane, it's just at the origin. So if I define some wave function that depends on the field configuration on this spatial slide, I can always back evolve to the infinite past And that state will corresponding some local operator on the complex plane side. Then you will see a very cute tutorial in string theory to make this correspondence more rigorous. But at least we don't have the same problem in QFT. This is just not possible, but because you can shrink things. So at x0 goes to minus infinity, CFT, conformal transformation, managed to claim a circle goes to a point. And I can put a local operator there. Hey, so that's exactly how we propose to define this in-state. We take an operator, and let's take the limit such that it goes to origin, and then act on the vacuum. And then we claim this local operator at the origin is corresponding to a state. Since the state happens to be at the infinite past, that's why we call it the in-state. Okay? Okay, done. Next step, what's the out-state? Well, I could just say that the in-state, if you take the complex conjugate, if you take the Hermitian conjugate dagger, well, I guess the out-state. Well, that doesn't tell us much, because I have to define what does this thing mean. Like, what do I mean by taking a CFT state and a Hermitian conjugated? So let's try to define that. There's one subtle thing. We go to Euclidean signature because everything is simpler. But in this particular case, there's something subtle, because if you take a Hermitian conjugate in QFT, what you realize is that the time doesn't really change, and the space doesn't really change. Other things changes, but the space-time is still space-time. But we are on Euclidean signature, so unfortunately our x0 is defined by IT. So if you want to keep the same idea that the space-time doesn't change, then your imaginary time must change. So in CFT, if the argument of the operator is z, which is defined to be x, this guy, which is our map to get it onto a plane, then according to the rule that t and x doesn't change, which tells us x0 gets to pick up a minus sign, while x1 is the space, which doesn't have to change. So this z now is going to e to the minus x0 plus ix1, which you can write it as x0 minus x1, 1 over. And you go to 1 over z bar. So whenever you have an operator has some z dependence, once you do this Hermitian conjugate thing, it'll become a 1 over z bar dependence. Just because we want to keep the same idea that t goes to t, x goes to x. Okay. So enlightened by that, I will attempt to define what does this mean. Now you realize that when I change this cat into bra, the vacuum is still going to be the vacuum, the bra vacuum. The only thing I really want to know is what happens if given me an operator, what happens if I do a Hermitian conjugate. And enlightened by what we just discovered, we know the argument had better be 1 over z bar, 1 over z. And there are some important prefactors that I'm not, at this point, I'm going to propose it to be this thing. And this is not a mistake. It is z bar to the 2h and z to the 2h bar. Okay, you're like, where did you get that from? It's a good question. So after you prepare some, initial state, and you have some final state. And a very simple question to ask is that, what will be this guy? Take an inner product of your in state and out state. Since that's how we define a Hermitian conjugate, that basically it's asking what's the norm of the in state. And that's, important questions in life. So let's do that. You get some vacuum state on the two sides. And then in the middle, you get this. And according to our rule over there, you get this. Let's say fun proposal says that we should have got this guy. And now you take the limit, everything goes to dz bar, w bar, all goes to 0. Okay. So now, well, I'll be sloppy in the sense that I can just take this guy to be 0, and hopefully it's well-defined at all. And for this guy, well, I can't really just replace them by 0, otherwise I'm writing a bunch of infinities, which doesn't tell me anything. But what I can definitely do, which we have done many times so far, is that I can always inverse the thing. That's a good thing about conformal transformation, that the inverse is one of the allowed transformation. So if I inverse this thing, what I get is replacing 1 over z by c, 1 over z bar by c bar. And now I'm taking c bar to infinity. It seems we're in trouble because we're taking things into infinity. But luckily, we have this very nice 2-point function there. Assuming we have a primary, then we happily write down this 2-point function must be d over c bar to the 2h, c to the 2h bar. That's just all the primary. Like we did it in the tutorial, all the primary operator will have this property. Okay, this is great. Because now infinity all cancel. What do we have left is some normalization constant, which is a finite. So the idea of defining that Hermitian conjugate with such interesting prefactors is precisely guarantee that when we look for the norm of our initial state, it's finite. Seems to be pretty good a reason. Okay. So the next thing we do is, well, this kind of be surprising to you. You got a field, and what's your next thing do? Let's do the mode expansion. Since we are unable to study the field as itself, it seems that studying the individual Laurent mode will reveal something exciting. So, motivated by the expansion we did yesterday, we're going to define the mode expansion to be z to the n plus h. So remember, that 2 comes from energy momentum tensor always have conformal weight 2. So if we want to expand the mode of phi z, we're going to expand with this plus h. And then you were like, but if I expand not with the plus h, it's still a valid mode expansion. But this will make life slightly easier in the following way. So first, we mode expand this guy. I become sloppy again and drop all the anti-holomorphic part, and hopefully they can be showed simply. The other half should work. So if you give me a Carroll field This is how I'm going to expand it. So now let me show you that this expansion is a very nice expansion by trying to figure out what's the Hermitian conjugate of this guy going to expand. Okay, so if I take the Hermitian conjugate of this guy, according to this, I should just take the mode Hermitian conjugated and take the Z and change it to the complex conjugate, which is Z bar. On the other hand, this guy was defined up there, says it should have been 1 over Z bar 2H phi evaluated 1 over Z bar. That's just the definition of phi diagram. This is, first line is take this expression and diagram. Okay, but now I can expand this guy according to this expansion proposed, which is sum over n, phi n, and now I have to replace Z by 1 over Z bar, which gives me Z bar to the n plus H. Okay? I'm just saying if you're expanding this guy this way, then this guy should be expanded this way. So let me collect terms. Oh, interesting. At least this magic is also time translation in there. Like I use it every day. But, okay, so the step is simple. You just collect the like terms. And now there is an interesting trick. Since n is infinity to minus infinity to infinity, so summing over n is no difference from summing over minus n. You still get to sample all of those guys. And if you compare this expression and this expression, you'll realize, oh, the Z bar dependence is the same. So we have phi n dagger is just phi minus n. So the following proposed mode expansion, why we like to expand our mode in that particular way by pulling the conformal weight out, is that if we define that way, we can happily say, well, the Hermitian conjugate operator's expansion, the mode expansion, is the same with a minus sign to the original. Make life easier. In particular, we're just doing expansion, so I could have just expanded our energy momentum tensor, which means energy momentors also have this cute relationship. Okay. So now we have some modes. And as we said at the beginning, then we can try to study what is this vacuum. Well, I still don't know. But the one thing I kind of want is that if I'm acting on the vacuum, and like the inflation is the free pizza thing, I do want my energy to be finite. Same thing to require. You have a vacuum, and I want to measure the energy, and I sort of want the result to be finite. And it has the following mode expansion. And then we run into similar problem. What if Z goes to 0? Then we have the problem says that if the problem occurs when n is bigger or equals to -1. Remember, n is just integer because it's a Laurent expansion. So n equals -2, it's still fine. We have z to the 0, which is 1. It's only when n is bigger, from -1 onward, this guy is going to cause trouble. So with a battery required, the other part goes to 0. So demanding that we have a finite energy gives us the condition that when n is bigger or equals to -1, all these modes should annihilate the vacuum. And then now I can just take the Hermitian conjugate and then see what happens to this guy. But remember, this guy is equals to this guy minus sign. Nice things in life we just discovered. Which means this must give us the requirement that when n smaller or equal to 1, that it annihilates the vacuum too. It annihilates the left vacuum. So it seems to be the same number. The generators that generates the global conformal symmetry seems to be annihilating our vacuum. And that's the conclusion about our vacuum. Okay. So, okay, very good. So now we have our setup. We have our initial state. We have final state. We have vacuum. We can start trying to build the entire Hilbert space. So there is fun fact. It's just something we're going to use later. Fun fact, if you do this commutator, so we're going to talk about this, you use this commutator later, so we're just going to do this. It says Ln is that the bar z n plus 1 tz phi w, and then we can use the OPE of t and w. And remember, this is the definition of the primary field, which gives me h phi on one term, and the other guy is the partial phi. And now I can just do the integral. The first guy says we need to take a derivative. The other guy says I can just read off whatever it is. Okay. So equipped with this, we can answer the following questions. So what we just studied is that what happens if I act this mode things, all this mode expansion, all this important generator else on vacuum, what happens? Now I can ask the questions, what happens if I acting on the in state we just built? So I bring the operator to the origin, act on 0, and produce a state. And now the question is, if I add all these L generators on the state, what do I get? So let's start with L0. So if I act L0 on this in state, which is defined to be L0 acting on phi 0, acting on vacuum, and we do our normal trick. Whenever we don't know what to do, we'll switch the two operator, and a commutator will show up. And this disappeared because our vacuum is annihilated by the 6 global generators. And this guy, according to here, when n equals 0, when n equals 0, and take the limit w goes to 0, so this is 1, and this is 1, so you get h phi back. And the other term, because n is 0, and take w goes to 0, you get nothing. And you realize, hey, I got my state back. So what we just showed is that the end state we define, it happens to be an eigenstate of L0. So remember, from like the first lecture, L0 is something like scaling. And the scaling in 2D is something like time translation. So H is something like energy. So from now on, I'm going to refer the conformal weight, H, always as the energy of the state. Because going in the radial direction is the same as going in the time direction. So now I can actually label this end state I used to do as a state H, which is just labeled by its eigenvalue under the energy operator. And the energy operator is L0. Okay. Now let's ask the question, what happens when I add Ln onto this state H? So let's only discuss when it's positive. So there is infinite number of n's. I can do the partition study 0, study positive, study negative. So let's study the positive guys. So the positive guys basically give me the same thing. I can even skip a step. Says that what I want to do is change it into a commutator plus this switch side. And according to our demand, a very thin one, says that we should have, oh, it's right here. We should have our energy momentum tensor to get finite result. That demand says that the Ln, when n is positive, will kill this guy. And this commutator we just did, but now n is bigger or equals to 1, and w is going to 0, so we get nothing. So H is such a state. Under L0, the energy operator, it has an eigenvalue of H. And all the positive modes will annihilate it. Okay? So now, let's study what about the other guys. Well, the other guys, if you look at this commutator, is not going to help us anymore because you get some. And when it's smaller, that expression doesn't look very. It's not very helpful. So we are going to ask a different question. So suppose now n is negative. Oh, it works for all the n's. But then let's ask the question is, what's the energy of this state? Since we have like one operator we use as a label to label our state. So now we wonder if we act on it with one of these negative modes, what's the new energy? This is, finally we can harvest our result of the algebra. The algebra tells us this commutator is L minus n. Sorry. Prefactor of minus n, Ln. And this guy is an eigenstate, so H pop out. then we realize we get H minus N, Ln acting on H. Cool. It says if we act with a negative mode, we still have an eigenstate of L0. Except, of course, the eigenvalue would change to H minus N. And since we're studying N negative, it means all these descendants, so these are called the descendant states because we start with a primary state, then it's generated by that guy. And then a good thing is that, look, H minus N and N is negative. Think about if N is positive, then it's not good. Energy just keep dropping. You really don't want this thing to work if N is positive. Then your energy is not bounded below. And happily, we showed it's okay. When N is positive, that this state doesn't exist. It only works for negative N, and it's going to increase our energy. Also makes sense. We have a vacuum, which is at the lowest energy. And if you you create some other, states out of the vacuum, out of this state, you get states have higher and higher energy. Sorry, that's not the vacuum have energy 0. So we build a state, which is sort of like the ground state, has like lowest energy, and then you can build a state above them that have higher energy. Okay. So now let's note. Okay, let me write this down. This is happy phase because our energy is bounded below. So, any questions while I'm moving more boards? No, it seems trivial. It's some commutator that's not hard. Okay, so what we have just seen is that we build a state. And this state is eigenstate of some state. What we further say is this state has the following property. It's annihilated by a bunch of operators. And when you use some other operators to act on it, the eigenvalue changes. Furthermore, you even have a relationship says these operators that annihilate them and the operator that make more states are harmoniously conjugate of each other. Does this remind you anything? Let me remind you that the OB1 is not our only hope. So this should remind you something. We have done this before. Something is the eigenstate of some operators. And this state has the following property. Some operators will annihilate it. If you use some other operators, you can make more states. So let me compare the following two algebra. One is something we attempt to study today, and one is something we're very, very, very familiar with. So we start out with, we have L0. L0 is something where you're using its eigenvalue to label states. So this must be our J3. Okay, I'm going to use N positive as the convention. So now I have Ln. These Ln's, it kills the state. So this must be corresponding to the raising operator. So these are G+. Well, we have many G+, but each of them are like G+. It acts on the high spin, it kills it. right? This acts on the lowest state, lowest energy. It tries to lower it further, but that's not allowed. It kills it. And then we have the negative guys. These are the lowering operator, which is G minus. So we have a state called H, which is the eigenstate of L0. And this is the highest weight, which, as I said, is a little misnomer. But we call the method of this whole method called the highest weight method of finding representation. So this corresponding to the guy with spin J, and it has maximum J spin. And it makes sense to call it the highest weight in this case. But in the case, this is the lowest energy. And then we say we can get all the rest of guys by acting lowering operator on this. You can have a bunch, as many as you want. You can just keep acting on this. This is like acting G minus on it. You get something like a generic state of Jn. Okay, there is a difference this time. In this case, you have constraints. It is half integer, and this one cut off at some point, and this one doesn't seem to be, so you can just just keep doing. But this is very similar. You always have the Cartan generator. So we can label our states. And then we have raising operators and lowering operators. Then we can use the highest weight state and then find all the rest of the states. So we have built our Hilbert space. Our Hilbert space says it looks like this. Whenever you hand me a primary field, then I will start out with level 0. We'll start with a highest weight state, which is H. And the level equals 1. Then I use this guy acting on H, and I get energy H plus 1. And then L equals 2. I can either act 2 of these guys on it, or 1 of the L minus 2 on it, then I get H plus 2. And in the next state, I can either act 3 of these guys, or 1 of this guy, 1 of that guy, acting on H, then I get H plus 3. Well, I can also act L minus 3 on. And actually, you can say, as the level go higher and higher, this is basically says, give you an integer and partition them. So there's going to be a huge degeneracy down there. You have like many ways of creating states, and they all share the same energy. So what you do is you go to L equals N, which you can say there is some partition of N. It's something like a minus N1 to L minus Nk, and all the sum of this N little things from 1 to K will give you the total level of N, and acting on H will give you H plus N. And then there is a degeneracy exactly equals to how many ways I can partition the integer N. So this is our Hilbert space. Come with a highest weight state and all its descendants. So mission accomplished. So now we're going to go the other way. So we find this descendant states. We begin to wonder, since we have this cute thing called a state local operator correspondence, what kind of operators do they correspond? After all, in the CFT, we always seek after the correlation function of operators. We know these states exist, but if we don't know which local operator they correspond to me, that doesn't help me with correlation function. Okay, so let's do that.
And how do So how do we know that we are not, it's like the same argument that this is covering the whole cube space, that we are not missing states in this ladder?
Well, if you have other primary field, then you will have some other states. But if you started with this primary field, you are going to cover all.
Okay.
And like one goal tomorrow is trying to show that in some happy cases, you even know how many primary fields. In principle, you could have as many as you want. But it happens the conformal symmetry is such a huge constraint, like have so many symmetry, you're just constraining everything. And you can find models that has only finite number of primary fields. Like it's only consistent. It's only consistent when you have, say, 2 fields. Well, no, we have identity. Class 2 non-trivial one. And that's the Ising 2D model. You have a spin, you have an energy, you have an identity, and that's the simplest 2D thing. And you can actually show that with all the constraints you impose, and that model will pop out. So, but today, let's continue. Says that we find some descendant states. It's good to know what are the descendant operators. These things are actually defined very formally. So I have been throwing things under the carpet because of the OPE for a long time. Let's try to recover them somewhat. Say that we'll recover them as dots, regular terms that I don't know how to calculate if I'm doing contour integrals. But supposedly, once the end of W is not infinitely close, somebody is going to be able to recover those regular terms. And now I'm happily using an equal sign instead of this operator OPE sign. So let's, a same thing. Why, so what do people do defining this descendant operator is that just say, I'm going to define this as a expansion because it's a primary field OPE. It starts with -2. And then we'll call whatever come up with here the descendant operator. So this is how this descendant operator is defined. It's defined that this descendant operator is the coefficient of the Laurent expansion of the T phi OPE. So this will make sense. That's just a hat to distinguish from the generator. So this makes sense because level 0, if you read it off from here, it gives itself. With the conformal weight, the more making sense part is the level 1 descendant is partial phi. So remember, last week, it's mentioned, how do you build a descendant state? You just keep acting momentum operator on it. Because momentum operator and the dilatation operator commutator give you give you -d. The momentum is like the raising operator or lowering operator of the dilatation. And dilatation is our energy. So if you get something like a partial phi, we should be happy. That's indeed what we get. So first level descendant is partial phi. And it's the level 2, if you continue this process, which depends on which particular operator you're talking about, the constant term will let you recover what would be the level 2 descendant, and so on and so forth. Here's a fun fact. Let's say one thing, let's say this thing once. The fun fact is that I want to know at least one second descendant to just have a flavor of it. And I've decided to use some OPE. But I already say this is a generic primary field. So there's not many options, except we still have identity. So let's check what's the OPE between TZ and identity. Well, let's claim that TZ times identity should equal TZ. Except I'm going to write it in a very funny way. It says that it's Z minus W2 squared. Since identity is an operator coming with conformal with 0, so that's 0. And since identity doesn't depend on CLW or whatever, partial identity is also 0. And then there's the finite term, which is TZ. And then the rest are also zeros. So according to this definition, this tells us the energy momentum tensor, the energy momentum Carroll field, is actually the second descendant of identity. It's just a cute fact. Okay, so now we come to close to the end of the class. So we are trying to show this miracle. So the miracle statement is we only care about the correlation functions of primary field. As a start, what we're going to try to see is what if I bring the T field, the energy momentum field, close to a correlation function. So it's an endpoint correlation function, but I'm going to bring TZ with some infinitesimal parameter in. So I'm considering this correlation function. So what we actually want to show is that if there's descendant field in the correlation function, it's related to the primary correlation function. Since the descendant field is defined through a T-phi OPE, so I'm going to just consider in general what happens if I bring a TZ with an arbitrary function close to a bunch of a primary field. So this guy, so I want to evaluate this guy and take the contour integral when Z is really, really big. So this is what we do. We have a plane. We have some like N operators everywhere. And I take a huge contour to circle them all and to put a TZ on this and then calculate what's this. And this guy says, well, remember we can always deform our contour. I'm going to deform this contour into a bunch of small contour, since the only thing we care is when there's an insertion. If there's no insertion, contour integral doesn't produce anything. It's like 2 days ago that trick, which Ned pointed out looked like a BB-8. But the point is that as long as you don't go across insertions, you can deform a contour any way you want. Which means, because this thing is supposed to be radial ordered, so I can say I bring the TZ close to this guy and do this contour, and bring the TZ next to the next guy, do the next contour, so this guy equals to a bunch of contour integrals when you're bringing the TZ close to 1 equals to some epsilon. So now we managed to bring the TZ next to a generic guy in the middle. So we're just going to do all the small contours right when they are close. And of course, the reason we always want to bring things close is to use the very powerful operator product expansion. Since this guy I can expand. I can use OPE to write it as the thing that we have written many times, which consists of this and the simple pole, and then some other dots, which are far away, hence we don't care. The only thing I do is that it's a time-ordered correlation function, so I'm going to explicitly make sure the time order is guaranteed, and then expand with OPE. And I can write this guy by taking this part out. So this guy, I'm losing my DC all the time. There. So the claim is this guy, I can just take this operator out. Because they are not a correlation function. So we should be able to first find the correlation function of this field and then act this differential operator on it, instead of doing the differential operator on the field and then find OP. Yes?
What is this epsilon of Z that you put inside the correlation function?
Very good. It's arbitrary.
Why did you put that?
Exactly. Why would I want that? Well, you put the arbitrary things so you can make the argument that since epsilon z is arbitrary, thus this two integral equal must be telling us the integrand are equal. So I just want to drop the contour integral. I introduce the contour integral so that I can make this the form of contours. But what I want to prove is not the one with the integral. What I really want to prove, or what I really want to state, is that if you bring TZ, do TZ a bunch of primary field operator, this is some differential operator like that onto a primary correlation function. So this is what I want to do. But in order to show that I want to use the contour integral trick we always have on the complex plane. But in order to drop the contour integral, I introduce this arbitrary function says, well, since this thing holds for arbitrary function, I must be able to drop the integral since this holds at the integrand level. Okay, so now we have this. And the next thing to do is take z goes to one of them, the last one, for example, and then do expansion. So when we bring TZ to this guy, we can use our expansion, that definition of the descendant. So on the left-hand side is going to be some summation of something. But the important thing is at the end of this guy, one of a series of this descendant will pop up. So on the left-hand side, as you will bring z equals to omega wn, and then use the definition, then a descendant appeared. On the other side, we do the same thing, except we say z minus wj must be able to write as this thing, And so I can expand all these things. So on the left-hand side, I have the descendant operator, the correlation function with bunch of primary and one descendant with some summation, which is equals to some horrible differential operators acting on correlation function only of the primary. So if you do this, you expand around the Wn, but on both sides, eventually you can, the conclusion is if the correlation function has one descendant in it, it is equals to some crazy differential operator acting on the primaries. And this thing is known. It's just, you can check the notes. It's just really long, as you can see that, and not very illuminating. But it's some known differential operator. So indeed, descendants, in some sense, they don't matter. If you want to understand their correlation functions, well, they are always equals to some differential operator acting on the primary correlation function. So we get our miracle. The only thing we care is the correlation function of the primary operator. So tomorrow, we're going to say we can make even better wishes. So tomorrow we want to do two things. First, to find what kind of constraints such that we can find these solvable CFTs that only have a finite number of primary fields. And then I should really answer my own question. What do I mean by solvable? Solvable means I can find all the correlation functions, which means I can give you a set of H, a set of Cijk, and it tells you exactly how these guys actually meet the crossing symmetry. It's non-trivial. If you give me a list of numbers that says, these are some conformal weight, these are some structure constant, normally that it doesn't work with the crossing symmetry. But there is a way to make it actually solvable. And the trick is, see, this is a differential operator acting on the correlation function. What is what we are seeking after? What if this guy happened to also be a primary? No, this guy happened to be a descendant, also happened to be a primary. And in that case, we can actually show this guy have a zero correlation function with everybody. So we're going to find that guy tomorrow. So basically, in very specific scenario, this thing can be under condition can be equals 0. So you actually can find a differential equation for all your correlation functions. Then I can claim I can solve it. It's horrible to ask Mathematica to solve it, but it's solvable. Okay, so I'll see you tomorrow.